attendance. That's number 76463. And so we're on time. Shut your laptops and all that. Here we go. So for those on Zoom, the attendance poll is Piazza Post 463. On. Okay. 8 o'clock. Everybody, laptop shut. Can you please? You're holding up the class. Okay. All right, morning, everybody. And this is the last of our lectures on training the neural network. I usually do manage to get through the entire lecture, but then if something spills over, I may actually take a little bit of Friday, but it's highly unlikely that it will. We're going to be covering some of the ideas of incremental learning, batch processing, and why momentum and other optimizers are required. So the recap, we've seen so far that neural networks are universal approximators, but they must be trained to approximate any function. And we train them to minimize the total error on a training set, which is quantified by a loss. And this is done through empirical risk minimization. We use variance of gradient descent for this purpose. So we also saw that vanilla gradient descent may be too slow or unstable. Better convergence can be obtained using second order methods, which we didn't actually cover in class, but which were there on your slides, that normalize variation across dimensions, and using adaptive or decaying learning rates that can improve convergence. And we also saw that methods like RProp, which decouple the dimensions, can improve convergence, and momentum methods which emphasize directions of steady improvement and de-emphasize unstable directions can also improve convergence. So we're going to be looking at incremental updates, trend algorithms, and some tricks of the trade, generalizations, activations, and normalization. So first, incremental updates. Here's how we trained a network. You were given some target function shown by the dotted line, or there was some target function shown by the dotted line that you would like your network to estimate, but you had to do so using only the training inputs shown by the lines. So there were a finite number of points at which you had input-output relationships, and you trained your network to minimize the error at these points, with the hope that if you did so, then it would actually minimize the error everywhere else. And the way you did it, you started with some initial function, and then the function itself could be evaluated at only these few training points. You found the error at each of the training points, and you found which way the gradient must be, which way the estimate must be adjusted to decrease the error at each of these training points by computing the gradient at each of these points. And so you would find, for instance, that the function must be pushed up here, pushed up here, pushed up here, down and down at those two places, and make an adjustment accordingly. That would give you a new function. And then once again, the new function is not going to be it. So again, you would find out which way to push the function at each of the training points. Adjust those, so it has to go up at those green lines and down at the red lines. And that gives you the new estimate. And you repeat the process till you get to till it converges. This is what you're supposed to be doing. This is what we will call the batch update. You have to look at all of the training points because you're trying to minimize the average error across all training points. Now, what would an issue be when you want to perform something of this kind? If you wanted to train in this manner, what is the biggest choke point that you see? Anyone? Julio?
It would just take a really long time to do.
You'd have to evaluate this at every point, right? You must process all training points before making a single adjustment because you're finding the error at all of these points and adjusting all of them. And this is not a great thing to be doing. So that gives us our first poke. Okay, so can you call out the name?
Silver seal.
Okay, silver seal. What's the answer? Silver seal? Yeah. What is the answer?
All correct.
All correct? I gave you the answer on the screen, didn't I? Okay, so all this turned out to be was making sure you were awake. Okay, thank you. But then, the actual loss function we try to minimize requires batch updates because the actual loss function, which is not the risk that we were trying to estimate, is the average divergence over all training points. And batch updates minimize the total loss over the training data, but they require processing the entire training data before we perform a single update, which is a challenge. So how could we improve on this in terms of making updates? Here's an alternative. So when we are trying to model a function, it's a bit like shaping putty to form some shape. And then there are multiple ways of doing it. The ideal way for you would be to have a robot arm with many different points and which molds the function all at once. But that's, as a human being, you couldn't do it. So if you were working with putty, how do you do it? Do you suddenly sprout 10 arms and push the putty all at once? No. What do? You poke it at one point, you poke it at another, you keep making adjustments. And the problem is that every time you poke it at one point, it pops out somewhere else. And you have to do this carefully so that eventually you get the shape that you want. And so shaping a function can be done in the same manner. You can adjust the function one training point at a time. Maybe you just check this training point. You find that the function that you currently have is below the target. And so you push the function up. Julio, can you shut your laptop? Thank you, right? So, and you push the function up a little bit. Then you pick up another point. You find it's still below. You push the function up at that over there. You find that it's pick up a third point. You're overshooting. Push the function down, and so on, right? But for this to work, you have to make these adjustments small because if you make giant adjustments, when you push something down at one point, the function is going to pop up at a different point. But so long as you do this, eventually, when you have processed all the training data, you would have processed that, you would have updated the function at every single training instance. And in this process, you could, in principle, have made greater overall adjustment than if you had performed batch update. So if I were to look at it in terms of pseudocode. Now, in the standard batch update, you would have gone through the entire training data before you had updated any single parameter. In this case, as you go through the training data, after each training instance, you will be updating the parameter. Now, this can be done iteratively, right? As you go through the data, after each instance, you will update the parameters. But then once you're done with all of the data, you can go back and revisit all the data and update the parameters all over again. So you will actually make multiple passes through the data. And each pass through the data is what we will call an epoch. So if you're learning your model, you're going to be doing this till convergence. Within each super iteration, which is what we call an epoch, you're passing over all of the data. And after each data instance, you're going to be adjusting your parameters. This is going to be done after each data instance. And there's some caveats. This kind of works. But then you have to be careful. Why? Consider an example like the one shown here, where my data are in two clumps. One clump to the far left, one clump to the far right. And now the shape of the function that you can learn is constrained by the model that you have. Now, if I were going through these data in serial order, if I process the data at the left in the beginning, it's going to push my function down at the left so that it matches the target function. But then it's going to pop up to the right. Then you proceed through the data, and then you find that you made error to the right, so you're going to push the function down there, but then now it's going to go back and pop up to the left. And this will keep on happening. It will keep cycling, and it will never really converge. So in this case, how could you fix this? Randomly, right? So what you would want to do is, instead, you want to go through the data randomly to get more convergent behavior. Maybe you pick some instance over there, push it down a little bit, then pick some instance to the right, push it down a little bit, and so long as you keep going through the data randomly, eventually you're going to get some kind of a balance and get to a solution, as opposed to going through it in the same order each time, in which case you're likely to get cyclic behavior, right? So if I were to look at it in terms of pseudocode, what does going through the data randomly mean? It means that each time you pass through the data, you're going to be passing. Firstly, you're going to be picking up random instances. Second, each time you pass through the data, you're going to be passing through it in a different order. Otherwise, it's eventually just cyclic behavior, cyclic selection of data, right? So that means between epochs, you're going to have to randomly permute your data. Selecting data randomly at each instance is essentially the same as permuting your data and going sequentially through it. So this is going to be critical for the whole thing to converge. So the story so far, in any gradient descent optimization problem, presenting data instances incrementally can be more effective than presenting them all at once. Why? Because if you're presenting them all at once, you have to process all of the data before you make a single update. Here, you're going to be making updates after every single data instance. So in the first case, you would have made processed all T training instances just to make a single update. In the second case, if you pass through the data once, you're going to be making T updates. Now, each of these updates will be smaller than in the first case. Nonetheless, cumulatively, you're going to end up with a larger final update. So this works provided the training data instances are processed in random order. So the order must be stochastic, which is why we call it stochastic gradient descent. And this principle is generic. It's nothing special for neural networks. You can use it anywhere. And for neural networks, it's particularly useful because of the massive amounts of training data we tend to train them with. Now, why does this process of incremental updates work? And under what conditions? For why, first, I'm going to give you a very simplistic explanation that's often given. Then in a little bit, we'll go and look at it a little more rigorously, right? So let's look at an extreme example. Now, what happens when I train the model on an entire collection of training data? I'm going to have a loss for each of the training instances. And the overall loss is the average of all of these instance losses. Now, each of these instance losses is a function all by itself, right? If I change the parameters, the loss on that instance is going to change. What we are computing is the average of many functions. So when I compute the gradient at any point, each of the training instances is going to have a different gradient. And the actual overall gradient that you use is going to be the average of all of these gradients. One training instance may say the error will go down if you go this way. The other training instance may say the error will go down if you go this way. So you take an average and you say maybe you go down this way, right? So that's basically what we are doing. Now, if all of our training data instances were identical, then what happens? If I were taking the average divergence over all the training data instances, is this going to be different than taking the divergence for a single data instance? No, right? It's going to be the same thing. And so after having processed all T data instances, you're making the same step that you would have had you had just one data instance, right? Now, does the same logic, would you expect the logic to completely break down and become different if the data instances are all slightly perturbed? So this is what we do. So if you had actually been in the, now, just to go back, if you had done a batch update, you'd be doing this, what we are showing on the picture to the left, which is after processing the entire data, you take a single step. Whereas if you were making incremental updates in a single step through the data, you're going to adjust the function a whole lot. But then here's the case, right? If my data instances were just slightly perturbed and not identical, would the logic break down? Or would you expect it to behave more or less the same? The function is smooth. You don't expect it to be vastly different, right? You still expect to gain if you're making updates after each data instance. Would you or would you not? Right? So now, if being very close to one another, if they were a little more scattered, would you still expect the same behavior?
No.
More or less, right? Eventually, when do you think the two are going to become equivalent, kind of? When your data have no structure and they're completely distributed over the entire space. The closer they are together, the more you expect them to correlate in some sense, the gradients to correlate. And so making updates after each instance is going to give you some benefits over waiting to process all the data before you make an update. That makes sense? Right? So it's a pretty good explanation, but there's more to it than that. Yes, Joshua?
So you're basically saying the more you randomly distribute the data points, the better approximation you're going to get.
Are you saying better, or the benefits over batch is what I'm speaking of, right? So over here, if all the data points are the same, making an update after just one data instance is going to be the same as making an update after processing all the data instances. So if I update after each data instance, I'm going to make a net benefit. I'm going to have a net gain over waiting to process all the data instances before I take a step. Correct? Now, if the data instances were not all identical, but just slightly perturbed, the same principle would more or less hold. That if I updated my parameters after each instance, it's going to be somewhat similar to this situation, right? And so the gap between the batch update, where I have to process everything before I take a step, and the incremental update, where I make updates after each instance, is going to keep increasing as the diversity of the data increases. And so in the limit, when things are fully scattered, you expect that this is where the benefits of incremental updates are going to be the least. That would be somewhat of a guess, right, Karthik?
So I had a question about you said the data is permitted for each instance.
Each iteration, each epoch.
Each epoch. So is it taken randomly from the entire data set, or are clumps taken together?
So no, it's you're permuting your entire data. You're selecting data randomly, right? Okay. Instances randomly. That's it. Just which is the same as permuting your data. So did this make sense to everybody? Right? You guys have to be nod a little more enthusiastically, please. Thank you. And so that's a bit of a hand-waving explanation. There's more to it than that. So let's go back and look at what are the considerations and how well does it work. First, we said the step sizes must be small, right? Why? Now consider a model of this kind. I have this training data, and I'm trying to fit a linear regression through it. A linear regression meaning that the regression line is going to go through origin. It's not affine, right? Just for illustration. Now, if I perform a batch estimate, and I looked at all of the training data and estimated found the regression that minimized the overall error, this is what you would get. On the other hand, if I were updating my estimate incrementally after each observation, so the batch update is going to be minimizing this total error. Whereas if I were updating after each observation, maybe that is the first observation, and this would be my linear regression, right? Then the next time around, I pick up that observation. That would be my linear regression. Then I pick up this guy, and that would be my linear regression. Is this ever going to converge? Yes or no?
No.
So when would it converge? What should I do to make it converge?
We need to shrink the learning rate.
Yeah, which one?
Normalize the data, put them together.
Normalize, no. So Kyle?
Need to shrink the learning rate.
So what you really want to do is to keep reducing the learning rate as you go through the data. So maybe the first time you swing all the way out here. The next time you don't go all the way to that data instance because you don't want to forget what you've already done, right? The third time around, you want to swing even less and even less. And so eventually, if you keep up with this with a decreasing learning rate, you're going to finally get to convergence. And this is actually provable, right? But are there constraints on the learning rate for this to happen? How fast must I shrink the learning rate? And is there an upper bound or a lower bound on how fast or how slowly these things must shrink? Now for this, we have to look at the topography of the space. So let's say you want to look at worst cases, because there's no guarantee that you're actually going to begin at anything other than the worst case, right? So let's say my optimal estimate is out here. Now, you're minimizing your loss function, and how are we minimizing the loss function? We are minimizing the loss function at each time in a proportionate to the derivative, right? So let's say my loss function for any given parameter, dl over dw, is always lesser than or equal to some c. So my derivative is bounded, which means my function is not arbitrarily steep. At some point, it doesn't get steeper, right? So then if I take a step eta I at any time, what is the largest amount by which my parameter is going to change? Anyone? C times eta I, right? Implies delta wi is lesser than or equal to c times eta I. Correct? Everybody with me? So now, if my initial point is here, and at each time, this delta wi is going to be lesser than or equal to eta I times c, correct? So delta w0 is going to be less than eta I times c, then delta w1 is going to be less than or equal to eta 1 times c. What is the upper bound on how much I'm moving as I move through time, as I move through the iterations?
N into eta n times no.
So summation I delta wi is going to be less than or equal to c times summation I eta I. You agree? Does it make sense? Right. And so this. Now, what is the worst case? How far away can you be from the optimum in the worst case? Infinite, correct? So what can you say about the sums of the step sizes? If I need to get to the optimum in the worst case, what can you tell me about the sequence of step sizes? The learning rates. Yeah. The sum has to be infinite, right? So requirement, summation I, eta I must be infinite for I equals 1 to infinity. Eventually, if I want to eventually get to the optimum, the sum of the learning rates must be infinite. Otherwise, if it's finite, I'm going to stop at some point and not be able to get any further. And I will not be able to get all the way to the optimum. Make sense to everybody? But there's a second requirement, and what is that? It's easy for the sum to be infinite if the step sizes are all constant. But do you want them to be constant? What do you want them to be? Decreasing. So you want them to converge. So the way that property tends to be this. You want summation I equals 1 to infinity. Eta I squared should be some constant, should be finite. So these are these two properties. The sum of the learning rates must be infinite, but the sum of the squares of the learning rates must be finite, right? So can you give me a function that has this property? A series, a sequence. 1 over eta squared. Eta is what you're trying to estimate, right? So can you give me a value for eta I which satisfies this property? Anybody? Guys.
You wanted to decrease, so 1 over m squared, I guess.
1 over, but then 1 over m squared. Will sum of 1 over m squared be infinite?
Oh,
No. So very close. What would be a good sequence? Anyone? What would be a good sequence? Saha, what would be a good sequence? Yes?
1 over n I, right?
1 over I, right? I can just say eta I equals 1 over I. This is your standard harmonic series. What is the sum of the harmonic sequence? Diverges. But what over I squared? That converges. So here you have a beautiful thing, right? So there are so typically you're going to look at sequences of this kind. You want your learning rates to be absolutely divergent but square summable. And so this is, you want the learning rate to shrink with iterations, which means that this guy is going to shrink with iterations. Of course, you still have to permute your estimates, your instances between epochs. And specifically, you want these two properties. The learning rates must sum to infinity, but they must be square summable. And the fastest converging series that satisfies both requirements is 1 over k, because summation 1 over k squared is definitely convergent, and in fact, summation I 1 over k tends to infinity, but 1 over k raised to alpha, where alpha is greater than 1, it can be 1.00000000001, that is going to sum, that is going to converge, right? So this is right at the boundary where anything else would diverge, and so that's actually a beautiful sequence, although there are other sequences, yes.
I don't understand how it came up with this condition of summation n eta squared should be converging. I thought the summation of eta should be converging.
Summation of eta should be divergent, right? Isn't that what we said? Out here. You wanted the summation delta I, W's, to be large enough to give from anywhere to anywhere. So summation delta W's must be capable of going to infinity, right? If the derivative is upper bounded, the only thing that's left with is the summation of the delta.
How did we get the second condition?
The second condition is that you want the steps to shrink regardless. And so for the steps to shrink, you need a second property.
Okay.
Right? And the second property that it actually comes out, that happens is that it must be square summable. Does that answer your question? Yes. Okay. So, any questions, kids? No. Okay. So we have these two properties, right? Now, here's a very nice simulated example. This was for k-means, where the authors, I've got this off the web, they have tried to perform k-means clustering. And in the first case, the green case, they have done batch updates. They process all of the data before they make an update. Now, k-means, as we know, is a random algorithm. The solution is going to depend on your initial clusters, initial centroids. So these dotted lines show you the variance in the loss across different runs. And the center is the average across different runs. And what we see is that in all cases, it converges to an error very close to 0. But then the amount of time taken starts off at something like 1.5 seconds. Now, on the other hand, if you make updates after each instance and you use stochastic gradient descent, you find that it converges much more quickly. It's done converging in 1/10 of the time that the batch update does. But what do we observe about the variance? Is it small or large? And what about the absolute loss? Has it obtained a loss as good as the batch update? No. So why is this happening? Right? So let's see why this happens. What we are finding is that the stochastic gradient descent method can converge much faster. Actually, there's a loss. There's a poem. Yeah. Okay. Time's up, guys. Lavender llama. Is the first statement true? Who's lavender llama? Lavender llama is absent. Okay. Bronze llama. We're going through the colors and animals. Bronze llama, who are you? Is the first statement, yes, is the first statement true?
Yes.
Okay, thank you. And gray owl, who's gray owl? Is the second statement true? Gray owl? Gray owl is absent, okay. Blue hippo, who's blue hippo? Yes, is the second statement true? Okay, thank you. And bronze shark, my good God. Okay, who's bronze shark? Bronze shark is absent, okay.
Blue leopard.
Blue leopard? Okay, I give up on you guys. So can somebody tell me the third statement is true?
Yes.
Yes.
And the fourth?
Yes.
Okay, so all are correct, right? Thank you. So let's try to explain this behavior. Why did we see what we just saw? Okay? And for this, let's go back and look at the loss function, the risk function that we actually wanted to minimize. The risk function we wanted to minimize was the expected divergence between the true and the estimated functions, right? And so here's what happens. This is my true function. Let's say this is my estimated function, right? At each point, I can compute a divergence. So if I look over the entire space, I'm going to get a divergence value at every point. This divergence has an expected value. What is the expected value? It's the average. It also has a variance, right? Because if I just plot the divergence is going to have some value at each point. And so this divergence function itself has a variance. Everyone with me? Okay. So now, the expected value is what we are trying to minimize, right? If you minimize the expected value, you're going to minimize the gap. Now, if I look at the loss function, the loss function is given by this. I have n training points. So I'm minimizing the divergence at each of my training points. But what is the expected value of this loss function? What do I mean by the expected value of a loss function? If I took different sets of n training points, each set of n training points is going to give me a different loss function, right? So if I had like 1,000 training points, I could collect 1,000 training points in 1 trillion different ways, right? Each of these would give me a different loss function. So the lady at the back in the green, if you're doing anything other than taking class notes, please don't. Okay, right? So each time you looked at 1,000 training points, you're going to get a different loss function. You can take an average across all of those. What would that average be? So that is like saying, what is the expected value of this guy? What is the expected value of my loss? That is simply going to be 1 over n summation I expected value of the divergence of xi. And the expected value of the divergence is simply a single value, right? Which is going to be 1 over n times expected value of divergence of xi. These cancel out. And so the expected value of my loss function is the same as the actual risk that I'm trying to minimize. This is the excuse that we use to be minimizing the empirical risk, the loss. And so, we're saying that we are minimizing some function whose expected value is the actual thing we are trying to minimize. And so we are fine. But then on the flip side, you have this situation where you could have now, what is the variance of this loss function? So if I took a different set of 1,000 training points each time, I'm going to get a different loss, right? The average of all of these losses is the true risk. But what is the variance? Each time it's going to be a different loss, right? So for that, I can look at it this way. I have 1 over n summation I divergence of xi. I'm trying to compute the variance of this guy, and which is going to be now, if each of my training data points is independent, what is the variance of a sum of random variables, independent random variables? Anyone remember?
The sum of the variances.
The sum of their variances. We know that the variance of x plus y equals variance x plus variance y if x and y are independent. Okay. You guys remember this? Right. So then I can write this, therefore, as 1 over n squared, because when I take a variance, this gets squared, times summation I variance of divergence of xi. And this is a fixed value. So this is going to be 1 over n squared times n times the variance of the divergence. I won't write the xi because I'm lazy. And this is simply going to be 1 over n times the variance of the divergence. So what this means is that if I take a lot of training data points and I compute the loss, if I look at the variance across all of these different sets of training data points, I'm going to get this variance is going to keep shrinking as my training data itself, the number of training data points itself increases, right? So that's basically what it says. And the factor by which it shrinks is going to be 1 over n. Everyone with me? Okay, so here, the empirical risk we saw, the expected value of the loss is the actual objective that we are trying to minimize. So we call this an unbiased estimate of the expected divergence. But the variance is 1 over n times the variance of the divergence of individual data points, right? So how does it affect us? At each iteration, so now if I'm performing batch updates, then I'm working on large batches, so the variance across different training sets is going to be quite small because n is a large number. Whereas if I'm working with stochastic gradient, at each point, I'm working on a single sample. So all I'm computing is a divergence at a single sample. And the expected value of that divergence is still going to be just what we want. So even for the stochastic gradient descent case, the expected value of the divergence, the sample divergence, is an unbiased estimate of the expected divergence. So it's an unbiased estimator, but the variance, because n over here is just 1, the variance of the loss that we are minimizing is going to be just the variance of the divergence itself, which is a much larger variance. Now, I'm giving you a lot of math, but I'll show this with pictures, okay? So what does all of this mean? I don't know how many of you understood the math. It's a lot of words. It's much cleaner to see this with pictures, right? So here's what we've got. I've got my desired function g of x. I have the current estimate f of x, right? I'm trying to minimize the error between the two. Now, I don't have the function everywhere. I just have the function at a small number of training points. So I'm going to be minimizing the gap between these two guys at these training points. And if I choose this particular set of training points, I'm going to say that the function must go up here and here, go up here and here, it must go down here, it must go down here, and it must go up here, right? And that is for 6 training points. But if I chose a different set of 6 training points, like these guys, what am I learning? I'm learning a completely different lesson, right? I'm learning that the function must go up everywhere. On the other hand, if I had chosen these training points, it's still 6 training points. What am I learning? I'm learning that the function must go down everywhere, right? So the specific set of training instances that I choose is going to give me a very different lesson about how I must update my function. How can I fix this? One way of fixing it? Anyone? Average? Well, no. I just have 6. I mean, average what? But this is over all the samples that I've chosen, right? So the simple way is to simply have lots and lots of training samples. If I have lots and lots of training samples, the risk of getting different lessons, completely different lessons from different different training sets is greatly reduced, right? So this is what we mean by saying that the variance of the loss goes down as you increase the number of training points, right? But then if I'm performing stochastic gradient descent, I get only one training instance, training sample at each time that I'm updating my function with respect to. So if this is my training sample, I'm going to say my function's just fine. There's nothing to do, right? On the other hand, if this is that guy, it's going to say my function is below where it needs to be and by a large value, right? And you're going to be adjusting it a huge way. On the other hand, if you got that single training instance somewhere else, you're going to get a completely different lesson. And so depending on the choice of training point, you're going to get wildly different hues across the samples, right? Which is why the variance of the loss is going to be huge. And that explains this figure. It does converge because you're making a lot more updates within each epoch. But because the variance of the loss is so wildly divergent, it's going to converge to a bad position, bad place. Right? This make sense? Okay, how would you fix this? I want the fast convergence, but I don't like this behavior. How would I fix it? Anyone?
Use batch size.
Use batch size, right? So what do you mean by that?
Like updates not after a single instant, but by multiple.
Correct, right? So SGD uses the gradient from only one sample at a time and is consequently high variance, but provides significantly quicker updates than batch. So is there a good medium? Here's what I can do. At each time, I can pick a small number of samples and update on these guys. And so long as the set of samples I choose at each update is random, I'm going to get better updates than if I'm using just one sample while almost getting the same benefit as having as considering the entire input batch. And so what must this step, so this is what we'll be doing. You'll be processing your data one batch at a time. You'd be averaging your divergence over the batch and then making your updates. Yeah? This is without replacement in this case. Think of it literally as just permuting. I mean, in principle, it should be with replacement, but in practice, doesn't matter. So think of it as randomly permuting your input and then chunking your input into blocks of size B, right? So what happens here? How would this help? Again, you're operating over batches. You have random permutation. You still need decreasing learning rate. You need decreasing learning rate because you're still working on batches which are not the entire data, training data. And the learning rate still has to satisfy the property that the sum of the learning rates must be divergent, but the sum of the squared learning rates must be convergent, right? And what we find is that if I look at the mini batch loss, this is what we call the mini batch, where you're averaging over small batches of inputs. If you take the expected mini batch loss, that is actually the true objective that we want to minimize. But then the real benefit comes in the variance, right? So for any batch of size n, our variance is going to be this guy. So this term here is the variance of the divergence itself, right? If you just look at the entire space and you compute the difference between the true and the estimated functions point by point and take its variance, that's some value. Now, as my batch size increases, this is going to be the variance at the divergence. And the mini batch variance is going to come down very quickly, right? It's going to come down as 1 over n. And at some point, you're going to hit the knee of the curve where the gap between this and this is not very large, right? But on the other hand, if you look at the batch size, the gap is huge. And so this is what you're taking advantage of, that the variance actually falls off as 1 over n. And so if you have a mini batch size that's large enough, you're close enough to what the variance that you would get with the entire training data, that you can just optimize over the mini batch and still get the same effect as training over the entire batch. But you're still going to be slightly off, right? But the difference is going to, because the number of updates you're going to make is so much larger, right? The ratio is this. The ratio is how many updates will you make in the time it takes to process the entire batch once. And so if the difference in variance is not small, but I'm going to get many more updates, you're overall much better off. That makes sense to everybody? And so what you'd really be considering are two variables. One is how far away from this variance over the entire batch will I be with my current mini batch size? And with the current mini batch size, how many updates will I make in one pass through the data? These are the two variables you must be looking at. And ideally, yes?
I'm assuming that is hybrid time.
Yes. Okay, so you want the variance to be as low as possible. So given sufficient data, ideally you're going to be taking, so again, there are two things to trade off, right? If the batch size is too large, yes, your variance is small, but you're making fewer updates, right? If the batch size is too small, the variance is large. So you want to choose a batch size where the difference between the variance at that batch size and the variance at the full batch size is not very much, and yet you manage to get a whole bunch of updates. It actually, unfortunately, the actual difference in variance depends on the variance of the divergence function itself. So it's hard to kind of figure out what's the optimal batch size. A rule of thumb is to make the batch size as large as you can possibly make it that will still fit in your memory, right? So, and here is the mini batch performance, and you can see how it performs comparably to full batch in terms of the loss and the variance, but it performs comparably to stochastic gradient descent when it comes to convergence. Right. Everybody with me? Okay. Okay, so I'll skip that. So in practice, training is usually performed using mini batches. The mini batch size is generally set to the largest that your hardware will support without compromising compute time. And convergence depends on learning rate. Okay. Again, the learning rate has to satisfy the properties that we just mentioned. And so, so the standard technique is to have a fixed learning rate till things have sort of stopped converging, then shrink it, and then it will converge a little more and so on. But in every case, you'll find that the learning rates are absolutely divergent and square summable. Okay. Okay, time's up. Green Panther. Who's Green Panther? So Green Panther is absent. Okay. Who's Apricot Wolf? Guys.
Here.
Okay. Can you tell me the answer?
Is it all of them except for the second?
Thank you. Right. Mini batch descent is an online version of batch updates as well. When the batch size is 1, it's the same as stochastic gradient descent, right? And then the variance decreases with batch size and approaches batch updates in variance, but SGD in efficiency when we use vector processing with large batches. So which is basically where we want to be. Questions? Yeah.
What does online version mean?
Online meaning as the data comes in. Right, so the story so far, stochastic gradient descent presents training data instances one at a time and can be more effective than full batch training if the data are provided randomly. For it to converge, the learning rate must shrink sufficiently rapidly with iterations. SGD estimates have higher variance than batch estimates. Mini batch updates operate over batches of instances. The estimates have lower variance than SGD. The convergence rate is theoretically worse than SGD actually, but we compensate by being able to perform batch processing. So the theory is a little bit fuzzy, but the intuition that you should hopefully have developed should work, right? Okay, let's move on to trend algorithms. One of the things that we have with working with these batch updates is that each batch is actually optimizing a completely different loss than each other batch because it's looking at a different collection of data instances. So this is where trend algorithms become even more important in that what happens is that even if you're computing the gradient, you're doing everything right, the gradient that you get from any given batch is going to be different from the gradient that you get from every other batch. So the loss function itself keeps changing as you're optimizing. And so in this case, this business of convergence becomes even more problematic. And this is where having momentum methods makes a lot more of a difference. In fact, you will see that the momentum method maintains a running average of all gradients until the current step. And we saw exactly what the momentum method is. By maintaining a running average, you sort of keep track of the gradients and keep them from swinging wildly. And once again, we saw that you could have both standard momentum or Nesterov's method, where in the standard momentum at each point, you computed a gradient and then added in a scaled version of the previous gradient. Instead, you could first take and extend your current step and then go against the gradient at the new position. And changing the order would give you a faster convergence, right? So we've seen these two. But then, okay, there's one more term. Wow, there's one more term in the update rule. What momentum methods do is to sort of adjust this derivative. Instead of simply using the current estimate of the derivative, the gradient, you're maintaining a running average of the gradient across many batches. And particularly when you're performing stochastic gradient descent or mini batch descent, this ends up being really, really important. So it smooths things out. But then if you look at the actual learning algorithm, the update rule says that I'm going to be updating W as W minus eta times the gradient. There are two terms that you can work with when you're trying to adjust your learning rule to account for the variations that occur when you have batch updates. The first, of course, is this guy. This is what momentum methods fix to reduce unstable oscillation. But then there's a second one, which is this term, the learning rate itself. So let's look at how the learning rate can be adapted. So I'm showing you 3 different examples. In all cases, if I were just to take the running average of the gradient, it's going to be more or less the same, right? But you consider the first guy, the net movement in the vertical direction is pretty much the same in all 3 cases, but where do you believe that movement most? In the first case, the second case, or the third? So if you look at the derivatives, right? The vertical derivatives are swinging pretty wildly in the last case. They were swinging much lesser in the first case, right? So if I were to use a learning rate, where would I use the largest learning rate? The largest learning rate would be the third one. Where would I be using it? Anyone? Why is there a doubt? So if I use a large learning rate over here, these are showing the derivatives, what would happen to my estimate? They're going to swing a whole lot more, right? Because things get scaled up. Whereas having a large learning rate over here is not going to make things so much, swing quite as much. So the more your derivative swings around, the less your learning rate must be to account for this wild swinging of the derivative, right? So how can we actually codify this? Here's how we can look at it. I can look at the total distance traveled, the total length of the derivatives. I'm actually going to look at the root mean squared value of the derivatives because, you know, if I just look at the scalar sum of the derivatives, they're going to cancel out in this case. So the scalar sum is the same in all 3 cases because the positive and negative swings average out. But I know that in the third case, the loss function has wild derivatives. It's swinging around crazily. It's very steep, right? So what I'm going to do is to compute the RMS value rather than the actual average of the derivatives. So here, if I have the x component of my derivatives and the y component, you can see the y component is swinging a whole lot more. If I took the squared sum of all of the y components and averaged them, right, and took the RMS value, it's going to be greater for the y component than for the x component. So effectively, here's what we do. I'm going to use a squared derivative. The notation I'm using partial squared instead of partial of d squared. It's not the square. The second derivative, it's the square of the derivative, right? And so I can maintain a partial squared running average of the squared derivative. And so this is going to be the mean squared value of the squared derivative. This is going to be maintained separately for each component. And so here is what we would do. This is your standard formula for maintaining computing the running average of the squared derivative, right? You have the current estimate. It's going to be the new, when a new value comes in, the updated estimate is going to be gamma times the current estimate plus 1 minus gamma times the new value. So that I would use that, and the actual learning rate is going to be inversely proportionate to this root mean squared value. Now, why does this make sense? If the RMS value is great, if it's very large, then it means that my estimate, my derivative is swinging wildly, right? And so I want the learning rate to be small. If the RMS value is small, my derivative is consistent. It's not swinging wildly, right? Maybe the derivative is small. Maybe I'm near a flat region. It's okay for me to take a slightly longer step. And so the learning rate itself is going to be inversely proportional to the RMS value. You have some initial step size eta. And so this is going to be done component by component. And you observe how now you are no longer adjusting the learning rate using any kind of schedule. The learning rate gets adjusted based on how the derivative has been behaving. So this is Hinton's RMS prop. And observe the similarity to R prop. Now, when we were doing R prop, we were using only the sign of the derivative, right? We were not actually considering the magnitude of the derivative. Now, if you're on a slope and the derivative is constant, then the RMS value is going to be the same as the magnitude of the derivative itself. And so if you're on a slope, these two terms will cancel out. This epsilon is just to prevent division by 0. So if you're on a slope, this bottom and the top are going to be the same. And if you're on a planar slope, because the derivative is always constant. And so the corrections are always going to be fixed step size, right? So this is, so R prop is always making corrections that only depend on the sign of the derivative. RMS prop will do the same if the function is just planar. But for more complicated functions, it actually makes updates that are inversely proportional to the RMS value of the derivative. So it sort of learns the appropriate learning rate step at each point. Any questions? So what we've seen is two things, right? First, we've seen that the momentum method maintains a running average of the gradient. The RMS prop maintains a running average of the RMS value. The momentum method stabilizes the gradient. RMS prop stabilizes the learning rate. So what is the obvious next thing? Do both, right? And if you do both, you get a familiar algorithm. Anybody know what it is? That's Adam, right? So that's basically it. So momentum only smooths out the gradient. RMS prop only adapts the learning rate, combine them both. And so in Adam, you actually maintain a running average of the derivative for each component. You also maintain a running average of the squared value of a squared derivative for each component. And the actual update is going to use the running average of the derivative with a learning rate that is inversely proportional to the RMS value of the derivative. So there's an extra term over here. There's this 1 minus delta to the k. This thing is just intended to make sure that in early, when you're early in the estimation process, things don't go haywire, because this tends to be a property. In that early on, typically, you're going to use a delta that's very close to 1, because you like things to be stable. If delta is very close to 1, what happens is that delta times 1 minus delta, you're not actually going to be updating your derivatives or RMS value very quickly. So it will take a very long time for this thing to actually become responsive. So this term over here, this denominator over here, is to ensure that in the early iterations, you actually respond quickly to the derivatives and the squared derivatives, and then only later on things become more stable. But the basic idea remains the same, that you're using a running average of the derivative on the one hand and a running average of the squared derivative on the other hand. The running average of the derivative is what you will use in lieu of the gradient, and the inverse of the RMS value is what you will use to scale down your learning rate, right? Both components are going to be adjusted. So, and there are other variants of this, of the same theme. Add a grad, add a delta, add a max. All of them tend to have the same kind of logic behind them. Okay. So questions. The next one is coral turtle. That would be you. Okay, so what's the answer? So vanilla SGD considers long-term trends of gradients. Does vanilla SGD consider long-term trends? No, okay. Momentum methods, do they consider long-term averages of derivatives? Yes or no?
Yes.
Okay. RMS prop only considers the second order moment of derivatives, but not their average trend. And Adam considers both, right? Okay. And trend-based optimizers are important to smooth out the variance of SGD and mini batch updates. True or false? True, right? So basic. Only the first thing is false. Okay. I have this bunch of Alec Radford has some very nice visualizations on his web page, which show how these different optimizers actually behave on different functions. This is something called Beal's function. And if you actually go over the function, you will find out how you can sort of look at the function and get an idea of how these things behave, right? So if you have something like atom or something like momentum. Now, if you have a flat surface, then the running average is the same as the derivative itself, right? And so you're going to expect things to, you do expect momentum methods to sort of behave, and both RMS prop and momentum to behave in a very steady manner. But when you begin combining these things, they behave in interesting ways. Here, for example, SGD simply gets stuck over here. And if you look at momentum, eventually it comes down. Nestrov's accelerated gradient is usually always the fastest to come down. So the thing is, you like these functions. All of these optimizers like these functions to not be steady. And SGD in particular is horrible. Anytime it finds a saddle point, it's just going to sit there. And in general, both Adam and Nestrov's accelerated gradient will find an optimum pretty quickly. Right? You can actually go through the visualizations. There are a couple of others. One more, right? Anyway, so convergence can be improved, we saw, using smoothed updates, RMS prop, and more advanced techniques, just to add to the lessons we've seen so far. Now, there was one somewhere along. How did I miss? I'm not sure what happened because I seem to have completely skipped batch norm. Okay, guys, I have a small problem. For some reason, my slides are missing batch norm. Give me a second. Is this the right one? Now we're good. Okay. I thought I was going too slowly, so I sped up. We're going to be covering batch norm in the next lecture, so we're fine. So what has happened is that I've sort of misjudged what I was covering. I should be more awake. So I sped through the lecture a bit faster than I should. I will come back and revisit batch norm in the next lecture. Well, you got let off early. Thank you. Any questions? It's just it's a different way of scaling things, right? I completely misjudged my content for the day because so I've been teaching since midnight. I had this my class in Abu Dhabi. No, it's a different. I'm teaching speech.